Welcome to my YouTube channel. In this video, we are going to learn how to solve the wave equation for electric field, which is giving us this expression, and as a result, we'll derive the expression for skin depth. So this equation is known as the wave equation for electric field components, and it's giving us equation 1, where this is our electric field, then relative permittivity, relative permeability, this is our conductivity, this is our del operator. Now, to solve this particular problem, we assume that our electric field, which is a function of time, is given by this expression. And we call this equation 2. Now, to solve this particular problem, we insert this expression into equation 1. And as a result, we have this expression in this. Still remains the same. For this part, we differentiate this one twice with respect to time, and we notice that our JW will now become squared, and remember that our J squared will become minus, and that minus and this minus becomes plus, so we have these parts. Then if we differentiate this one once with respect to time, we will get these other parts containing the complex number, which is equal to 0. So this is the next, this is the expression next, which is equation 3. From equation 3, it describes the behavior of the partial electric field in a conducting medium. If it is traveling in the z direction, then this equation 3 will reduce to this expression, where we are going to be considering only the z components, which is this. This one remains this, and this one remains this. Usually our r is supposed to take the value of z, our r is supposed to take the value of z. Now, because this expression, this differential equation, contains a complex number, then we assume a solution of this form. And in that solution, it must also contain a complex number. Take note that this expression is a constant that was brought in. Our aim is to determine the value of gamma for us to be able to solve this particular problem. Once we know the value of gamma, then we are done. Okay, so we substitute the value of gamma into the equation, the previous equation, and we'll get this expression. Remember, the first part has to do with d squared e dz squared. So we'll differentiate it twice, we'll get this part. But this one, nothing is done to it, we leave it. This part, nothing is done to it, which is equal to 0. Now our j squared will give us minus gamma squared. Remember, all these ones, they are the same. They will take care of each other. They will cancel out, leaving gamma squared minus gamma squared plus w squared e mu plus the complex number equal to 0. So we'll call this part equation 6. Now we'll make this one a Sebian formula, and it gives us this expression. Remember that our aim is to determine the value of gamma. From this expression, we can tell that this expression here, gamma, is going to be a complex number, because gamma squared is already equal to this expression plus the complex parts. So we can say this part is a real part, this part is a complex part. So from this point where we have our gamma squared equal to this, we observe that it's a complex number, and as a result, we can infer that gamma is going to be equal to alpha plus jp, where this expression is the expression for a complex number. So now, we now see that our gamma is now in terms of two new parameters, alpha and beta. So our headache now is no longer going to be on how to determine the gamma, but how to determine our alpha and beta. So if we square this one, and why are we squaring it? Because there is squared here. So if we square this one, it means we will square this one, which will give us this expression and this expression. Finally, we'll get this expression. Now, we'll bring out all the ones that are complex numbers and the ones that are real numbers. So these parts here represent the real numbers, and this part here represent the complex number. So we can now compare this expression, equation 8, to that of equation this equation. So we can see that alpha squared minus beta squared is exactly equal to this expression, while these two alpha beta will be equal to wg mu. which is this expression. Next, so from this point that we have, we now notice that we have two different equations to determine two unknowns, alpha and beta. So whatever technique you want to apply, you can apply. But in this video, we are going to be using the substitution method to determine the value of alpha and beta. So from here, we can make alpha the subject formula, and alpha will now become WG mu all over what? 2 beta. So with that expression, we can now substitute it into this place and determine the value of beta. So now I've made my alpha the subject formula, which is equal to WG mu all over 2 beta. So if you substitute that expression as alpha into this expression, we'll get this expression. Now we can square this, which is this, square this denominator, which is 4 beta squared, multiply everything by beta squared, and we are left with what? This expression. Now that we have this expression, we can resimplify so that it will now become b raised to power 4 coming to this side plus this minus this part. So it gives us this equation. So from this equation, we can assume that if we can let p equal to beta squared, so that this equation will reduce to this equation. Now we assume that this expression is equal to this expression where g mu w is equal to k, and with this we have this expression, which is the almighty formula for quadratic equation. This part is my b, this part is my c. So if I substitute into this expression, I'll be getting this expression here. Now at this point, it is important for us to know that our g is far greater than what? The multiplication of these two, because the multiplication of these two is equal to 1 all over the square of the speed of light. 1 all over the square of the speed of light. So if this expression here is far greater than this, then we can imagine that this one does not exist, and it will now lead to the square root of just this expression. The square root of this expression is just WG mu. If you compare WG mu with this, you can see that G is still inside of this part. G here is still going to be compared with this, which is still greater than this one. So at the long run, we'll discover that this part will still become useless. So our P will become what? WG mu all over 2, which is in the next slide. So, and this is what we've stated earlier on, that G is far greater than E mu. So we now have our P equal to WG mu all over 2, where beta squared, which is equal to P, is equal to this. So our beta is equal to this. Now since alpha is equal to this expression, so wherever I see my beta, I replace with this expression. So my beta is equal to, this one is 1 all over beta. 1 all over beta is 2 all over this expression, which is this. So I can resimplify this one to this, which is the same as square root of all this squared, all this squared. These two will cancel this squared, one of it. This one will cancel one of it. So our alpha is equal to this. So if you compare this with this one, you notice that alpha is exactly equal to beta. Okay. So we can now rewrite our expression, which is the original equation that we are trying to solve, as this expression. So wherever you see our gamma, you replace with alpha plus g beta. And wherever you see your alpha, you can replace with beta. And this is the expression. So the time part of the time dependent part of the electric field E is given as this. You just introduce your E equals E raised by JWT. So if you resimplify this expression, it gives us this full length. So what we'll notice is that there is J here and there is J here, and that's a complex number. We can bring this one and this one together, and take note that our J squared here is equal to minus. So this one is equal to this, while this and this will lead to this one. So this is the solution to the original equation that we solved, that we showed in the last slide. Now it's important for us to know that this part is a sinusoidal wave, is a sinusoidal function, and this one is a decaying function. Our beta here is equal to 1 all over Dirac, where Dirac is known as the skin depth. And how is beta equal to 1 all over Dirac? When you see this expression, e raised power minus any expression, and there is no complex number there, it shows that the multiplication of these two must give us a constant without any unit. So if Z has a unit of meters, that means this one must have a unit of per meter, so that per meter will cancel this, and this term here will become constant. That is, it has no unit. So that's why we say that this are beta, which is equal to per meter, will be equal to 1 over Dirac, where this Dirac is called the skin depth. So now this is a graphical illustration of the last equation that we showed in the last slide, where this part, if you plot this particular function, it's going to be a sinusoidal wave. If you plot only this part, it will be a decaying function. Now, if you now combine these two, which is the final equation we got in the last slide, it's going to now look like this. It's going to look like this. And what we now notice is that this particular electric field will die down as it enters a conducting medium. As it enters a conducting medium, it will die down. And that particular length that it will take is called the skin depth. Like, share, and subscribe to my YouTube channel. Thank you.